What up?
Much. How are you?
I'm just doing cars.
Uh-huh.
Hopefully my crystallized intelligence of the other three sections hasn't evaporated. I've
It,
only been reading about I've only been reading a lot of before Christ or whatever vernacular. So
yeah.
I hope I can even read the rest of the exam when I
Yeah,
do
yeah.
it.
Yeah, that makes me think of like there's something called, I mean, like this is something that I should have perhaps told you about a long time ago, but there's something called a Doolin back test. You ever heard of that?
Yeah, I think I read about that in your
Oh,
MCAT 526 manifesto.
got it. So,
Yeah,
um, but anyway, yeah, let's have you you know,
yeah.
pull up that next passage. So now, yeah.
Wait a minute. You want me to pull up a new three passages or the one I want to go over?
Oh, yeah, a new one. I mean, it
Okay.
may not be a new one. It might be one that you've just done a long time ago. But I think wherever you're up to for the uh I think I thought it was like the diagnostic tool that you still had.
Exactly. So I have like two or three passages left in diagnostic tool, but I think one of them is like really wonky. It's like 10 questions. So there's also the like official guide. It's like more questions that are provided and they have a cars
So
and it's
go to the diag tool. I just want to see that for a sec, like whatever you're up to on that.
okay. Yeah. So there's like I think three passages.
Huh? Yep. Hit open with JW. Okay. Now, like do you feel opposed to doing this?
Uh, I don't feel opposed at all. It's just the next passage is 10 questions. Also, I will say I remember doing this passage,
Which one?
like this 10 question passage, and I did like
Sure.
actually pretty well on it.
Yeah. So the one.
And there's this one I like went through two different times, so I would not like to do this.
Okay. And the first one that we just saw
Yes.
is
Yes.
is that one that.
We could do that. We could do that. It's on the yeah, we could do
Wait,
that. Sure.
what are you gonna say?
What I was gonna say is I think the the independent like official guide, whatever it's called, that car section I struggle with maybe slightly more. I remember in the past, which is why I wanted to go over that as well. But like we could do this if you want to do the diagnostic tool.
Is this a passage you like done somewhat recently?
I've done all these recently, but I'm not really gonna remember it. How about this? How about we do this?
Uh,
I think this is more up the alley of
let's see. For Okay, so yeah, so all right, so we're gonna have you. Um, when you say more up the alley, you feel like it's gonna be. Is it
Topper. Yes.
the other one you're gonna say it's too easy, right?
I'm refusing to say something is easy for me. This is cars, so it's harder. Like it's my hardest section. So I am gonna do whatever you tell me to do. It's just this passage is a little harder than the other one, but
Okay.
you choose.
So yeah, but like you don't remember the answers or any of that stuff. Okay,
Don't remember the answers for any of these.
okay. So this is what we're gonna do. Yeah, we're gonna do the one that you already have up over here,
Okay?
and we're going to have you do it do it the way that you would do it basically on the test, and I will be observing.
Hmm.
Okay, okay, so how is your default mode now going to be? Like, I know it's not completely like what we talked about with pausing and stuff, but I also know it's not completely just you rushing through anymore. So how would you describe your strat right now?
So, um, usually what I do is like I give myself around 10 minutes per passage, give or take.
Did you give yourself
My I give myself 10 minutes per passage, give or take. So
oh,
like if it's a longer passage, maybe it's longer.
for sure.
Um, but I watch the clock sometimes, but I read through. What I used to do is I would finish reading around 4 minutes. The last 2 days I've been doing each passage, reading it around five. And when I catch myself not understanding what I'm reading, like it's just like in one ear, out the other, I reread it, and if it doesn't stick, I just continue reading. Now, also after like two paragraphs, for example, I go from top to bottom instead of then the paragraph back to the beginning. I go from the top, beginning of the whole paragraph down and make sure I'm understanding what the author is saying. And at the very end of reading the article, I try to think to myself, like in a sentence or two, what was the main repeated idea, the main idea. And then I move on towards the questions. Um, I read the question, try my best to think about what they're really asking me, then go on to the answers. Sometimes I instinctively straight away go to the answers, but like I try to catch myself. If I'm really not understanding what the question is asking, I flag for review and move on. And hopefully, when I come back to that question, when I'm done with all the other ones in that passage, it's giving me a new look, and I'm able to get the answer.
Okay. So we're gonna have you read like not out loud this time, as if it's a test. And but when you're finished reading the passage though, like just verbally let me know. Just say like, okay, I'm done with the passage. And you do the questions. And once we finish the questions, like don't, hit solution or whatever. I'll let you know what we're gonna do after that. So, but yeah, we're essentially just gonna have you do it the way that you would normally do it, as if I'm not here. Um, and let me know when you are going to start.
So I have a question. Is
Yes.
there like what is the time looking like? I mean, I'm just doing it like slowly
We're
or
doing it the way that you would on the exam, although like I guess you're not going to see the time aspect of it. Uh, but go for it anyway.
and when I finish reading, I tell you or when I finish reading and okay.
But
Oh,
yeah, so when you finish reading the passage, let me know, and then go to the questions.
okay.
And then yeah, tell me when you're done with the questions. So I mean, so that could include like let's say one question you flag, you go on to the next one and you answer those, and then you can come back to the flagged one, whatever. But yeah, let me know when you're done with that. Um and and yeah, let me know when you're going to begin. And
Okay.
yep,
I'm going to begin.
go.
Jesus, I'm done. I don't know if you're here, but done
I'm,
reading.
I'm here.
Okay. And now I do the questions.
Yep.
Okay, I'm done.
Got it. Let me. This is the first question. Let me see um the one after that. Sorry, for 167. Okay.
The next is 168, or did you want to?
Yeah, 168 was what was it? Okay.
I like remembered the questions a bit from when I did it, I will say.
Okay.
But not to an extreme degree. I mean, the passage when I read it, it was like I
Uh,
completely forgot
Okay.
it.
Well, you crushed it. You got it. You got it all, everything right,
Okay.
and it was overall 10 minutes.
Oh wow. I
And
wow.
so the like so yeah, I was kind of looking for a distribution like this, meaning you spent so paragraph one, 1 minute, paragraph two, 2 minutes, paragraph three, 3 minutes, um, paragraph four, I think was like 1 minute. So it was around yeah, like 7 minutes total for the passage, but you were able to do the questions super, super, super fast. And that was kind of like what I was looking for, like uh meaning like if you spend more time on like the passage, even without realizing it, uh, and you understand it, the questions are really, really quick. So that's pretty good. And I just want to do that one more time with any, you know, passage that you want. Having less memory of it, of course, helps.
It has to be from the diagnostic tool, right?
It could be from anything. Like the something that's less familiar.
Yeah, there's a passage that I know like this one I haven't touched in a while.
Mhm.
So wait, not this. Wait. Yeah, I think it's this. Okay. But give me 1 sec. I'll be right back. 1 minute.
Yeah.
Okay. So same thing.
Yeah.
Okay. All right.
Let me know when you're ready.
I'm ready.
Go. So you're done with the passage reading?
I was literally about to unmute and tell you.
No.
Right? Like I remember.
Yep, yep.
Okay, I'm done.
All right, let me take a look at your choices from 6. Okay, 7, 8, 9, 10, 11. Well, guess what?
What?
Yeah, you got them all right.
Wow, really? But what was the timing?
This time the timing was a little bit more. It's
Yeah.
5:46 for the reading and 6 for the questions. So it's like around like 11.
I mean, 11, 12 minutes, I feel like it's kind of unrealistic for t like. I mean, like, yeah, it goes back to the accuracy statement you made, but yeah, that's surprising. This passage felt tougher. Honestly, the actual passage reading it was for me easier than the previous one, but the questions here were definitely more like,
Yeah,
you
so
know,
I'll tell you what I observed. So your reading it was fine. For the questions, I think you like kind of like thought through like the questions for a lot of these, and you kind of like move on to like the next one, and then you look through that question, and you moved on to another one. So I think that if you were to like slightly change something, like it could be like when you choose an answer to like kind of like if you're uncertain, flag it, move on. And if you don't know, like guess, flag, move on instead of leaving it blank.
okay,
But still really, really good. So now I just want to do one more with that passage that had like more than whatever, 5 or 6 questions.
sure. Okay, let's do it.
All right, let me know when you're ready.
Uh, Wait,
Yeah,
I'm gonna go use the bathroom real quick again.
yeah, go ahead.
One sec. Okay. All right.
Yeah, let me know when you're ready.
I'm ready.
Go.
I kind of remember the main idea here. Should I still do this passage? Like to an extent. It just feels almost like unfair doing it.
Uh, go for it anyway.
Okay. I'm done reading.
Got it. Got it. You're done?
No, like 30 seconds.
Okay.
Okay, I'm done.
Okay. How was
Uh, what?
how was it?
There was one question I remembered the answer. The other ones, like, it was still like I remembered some of the passage. I did, but
Yeah.
yeah,
Which question did you feel like you remembered?
this one here.
Which one? 150.
Sorry, one sec. This one.
Oh, 155.
Yeah.
Okay. Now, any questions that you're really kind of like stuck on?
Um, so the first one, I I went C, but partially I was like thinking about A. That I was a little stuck on this one.
Okay. Um, what about tell me about 148 and tell me about 150?
Well, 148.
Oh, we talked about 148. Oh, wait, did we? No, we didn't.
No, we didn't.
Oh, okay.
So 148, the way I interpret it is like it's what the female author is.
Oh, I'm just asking, like, was this particular, like, was this question like particularly difficult compared to the others?
Um, I mean, like, I guess, yeah, because I went back to it. I
Okay,
just wasn't, sh yeah.
sure. And then for 150, how are you about this one in terms of difficulty?
I think it was fine.
Okay. Yeah, so you got them all right.
Okay.
And it took about 11 to 12 minutes, which is the same as the other ones, except for the first one, which was like 10 minutes, 8 seconds. Now, given that this is a passage that has 10 like freaking questions, you were able to adapt to that because for this passage, all of the questions other than the ones I asked, 148 and 150, all of these other questions you answered in around 40 seconds.
Mhm.
Because I mean, if we were to do 1 minute a question, that would have already been 10 minutes, right?
Mhm.
So like ultimately the what I was like pretty much trying to look for, right, is like how to well, I looked for a lot of things. Um, but you kind of like fix everything. Like I was gonna like I was looking at like your your like eyes to see like if you're like reading it and then going back and all of that stuff, but you're essentially taking your time as you read. In all of these, you spent more time reading than answering the questions, which I think is ideal. You took your time with the questions as well. You like immediately started to eliminate things to go to 50-50. Yeah, you were able to really uh do really well. So, uh, meaning like without you found a pace, it seems, where you're able to complete the passage in time and have your accuracy be really, really high. Like I know that some of the passages, like the middle, like the second one we did was like 12 minutes, and then this one's like a little bit like 11 minutes. Um, but you can see that in like the first passage that the first passage that we just did, uh, could have been a little bit like so I guess in terms of improving speed, the only thing that um or the best thing that I think for you that I noticed from these is that so, like a lot of times when you choose an answer, you kind of like stick around and you kind of like you can, move on a bit and then you kind of come back to it after. And I know that you're doing it obviously to, check your answer. But if there's anything to out of like reading the like time it takes to read the passage, time it takes to read the question, time it takes to go through the choices, um, and all that stuff, like if you are to like remove some time, I think it should be when you have an answer chosen and especially when other choices are like eliminated, and you make your choice, um to just kind of like move on right away. So but yeah, all in all, you crushed it. You were reading it like for this, um first paragraph was 3 minutes 30 seconds, second paragraph was a minute, and then the third one was a minute as well. So you're showing me that when a passage requires you to spend more time, like this first paragraph is not just longer, it's like there's so much going on in it that you're able to give it the appropriate time. And then paragraphs 2 and 3, you were able to adjust to make it so that it's like a lot less because it took you a five. You actually finished this passage faster than the other two.
Yeah, this one I just remembered a little more better.
Yeah.
So,
So
okay, here's the issue. Here's the issue.
yes, yes.
This is a really big issue that I think honestly like
Mhm.
it screws me a lot on
Yeah.
cars, actual exams.
Uh-huh.
And this is what you're alluding to like tomorrow maybe. When I sense that things are kind of falling apart and
Yeah.
like I start getting anxious and
Uh-huh.
I start getting like the time thing starts like I realize I'm off time and like like
Yeah, yeah,
whatever. It's bad because I like revert to my old ways and start like frantically looking back to the passage.
yeah.
And I've noticed that like it's
Yeah.
hard to control sometimes. It's like the walls are like closing on me, like I'm getting
Yeah.
anxious and I just start looking back and eating even more. It's like a positive feedback loop, but like in a bad way.
Yeah, yeah, yeah.
I don't know how to fix that.
Got it. So let's say like, yeah, no matter what, like you're just in a bad situation, you're running out of time, there's no, what to do. So like some of the things that you can do is maybe like 3 paragraphs in, start like so first of all, start to look for those repeated ideas early on. So if you get like if it's a passage that has like 6 or 7 paragraphs, like 3 paragraphs into it, um, see if there's anything that's repeated. That can be one thing, to kind of like give you some type of hint at the main idea. 3 paragraphs in, let's say like that's like halfway in or 1/3 in, so that you have something that you see that's repeated, and then in the subsequent paragraphs, you're gonna look to see if it's repeated. So that's one thing. Another thing would be so like if you like pull up a random passage, doesn't have to like we're not gonna actually like read it, but I'll kind of show you what I mean, like a emergency contingency. for analyzing a passage would be like this. So you read like the first sentence of a paragraph, and that paragraph should be like, and of course, this is not going to be 100% or even close to 100%, but usually the first sentence of a paragraph will basically kind of like summarize that paragraph unless that paragraph has a contrast word. If it has a contrast word, pay attention to what's after that contrast word, and then you can kind of move forward that way. So like for this first paragraph, it's talking about like there's this discovery and people are talking about it. And then we have a contrast word saying that this has given it some type of certain fame. So, like right there, I'm just going to think this is something that was discovered, and the news of the discovery and I guess the controversy is making it have some fame. So that's what I would just do from that first paragraph. Um, and like for the subsequent paragraphs, like for paragraph two, I see that it's kind of just talking about like I guess who might have created it, but I don't see any contrast words, so I'm gonna just keep going. I'm gonna just keep going forward. Paragraph three, I see that they're talking about, or he's talking about, there's like all these footprints and scattered cigarette butts and litter and stuff like that. And that starts to be introducing something a little bit new because so far we've just been talking about this is an old hut. We don't really know who made it. And it's starting to become more famous. Now we see that it's starting to have a lot of litter and garbage and things like that. And if you were just reading them in a disjointed way, you would just treat that as something new. But if you connect it to what you're reading, you can kind of see like, okay, if it's more famous, more people are going to go there. If more people go there, there's going to be more litter. And then I would just continue moving forward. And then paragraph four, he talks about he's looking through like the fence that they made, no contrast words. So, okay, like the fence is going to be there to like protect it. And then the paragraph after that, whatever. He says, I didn't go back, but then we have a contrast word. I didn't forget it either. And he talks about how, is there going to be some possible time when people can view this like amazing discovery without like littering and destroying it? Kind of brings that up. So, but yeah, I'm looking at that paragraph as paragraph with the first sentence, but then I have a contrast word, so we're shifting things for that contrast word. Um, and so yeah, so this could be something that you can do if you're like super running out of time and you just don't have enough time to like do the full read through. Yeah, I would just read because most of the time the first part of the paragraph will be introducing a new idea and the rest of the paragraph would be supporting that new idea unless there's a contrast word.
Mhm.
So if you're really running out of time, you could try something like that, where you just pay special attention to the first sentence of each paragraph, and then whether or not there's a contrast word within that paragraph. If there's a contrast word within that paragraph, then it's going to be like different than whatever that first sentence is saying. That's just one of the things. The like contingencies kind of thing. Um,
Okay. I just I've never gotten 100% three passages in a row, no matter what. If even if I did a passage before, there's certain mistakes I make the second round, second time doing it again. So I'm very surprised. Obviously, I got 100% three times in a row, but like, I mean, what is even your take? Like, I mean, I'm technically switching my strategy a bit, and I haven't even tried on an actual full length. So
well, your strategy isn't
not, yeah.
too different. It's just that you're spending a little bit more time to think about it, which you were able to kind of show me like today. Now in terms of full lengths or whatever, like your the car stuff that you've been doing like the past few days have already like you've already improved tremendously from that. Like I think you're using like you found that balance. Like I was expecting for us to have there's a lot of things I was expecting today. Like I was expecting like for you to like not think about the question first, and then I was gonna do things like interruptions and be like, okay, like like three when you finish with the third paragraph, I was gonna be like, okay, what are we saying so far? Or when you're going to the questions, and if I was gonna expect to see you either like go straight to the passage or kind of like stick around and kind of like go through each of the choices. And then I would have said like, okay, like what's your own answer to this? But basically, yeah, so this and then like all of the work that you've been doing, like with the passages that you've been sending me, like you're getting a ton of them right. So yeah, so you're first of all, yeah, you're not really doing a different strategy, right? You're kind of doing the same strategy, except you're just allowing yourself to think. So
Yeah.
and so I think that's the big like it was always going to be like an easy change because for it just like literally just like okay just think when you think about it you get it right and that's not the case with everybody so but it's the case with you and that is good that's a really good thing um so uh so yeah so basically when you take your test do it the way that you did this and if you get to the point or something like that where you're just like super like there's nothing you can do and you're running out of time and all of that stuff, I think you can use kind of like that contingency that I described that I'll tell you more about like tomorrow, but also in terms of if there's anything like reading the passage, answering the questions, checking the questions, all of that stuff, if there's anything that I would say uh that you can shave off, like, the time that you spend would be when you answer a question, like you answered it. If you're not sure about it, you flag it. But no matter what, once you already click an answer, move on. So
Okay.
if you're unsure about it, so if you click it and you're unsure, hit flag, move on. If you click it and you're sure, move on. But a lot of times for like the questions that I wrote down, like so a lot of these questions like in the uh when you first answered like 147 and 149, it's like 40 seconds. Um but then you kind of like stick around or you come back to it. So I think yeah, if there's anything to do to help save time, it would be when you choose an answer, just move on. If it's something you're not sure of, flag it. If you're sure of it, don't flag it. But you don't want to just pick something and then like kind of stick around. I know you want to do it to like check, to check to see if you're right. But I think from what I've seen today that your instincts have like I did not see you change an answer from a right answer to a wrong answer. I did see you like eliminate two choices and not answer it and move or go to the next question or whatever, which is fine. But I would just guess something and then move on, just in case worst case scenario, you run out of time. That way you don't have anything left blank. But all in all, yeah, you've improved tremendously in the past couple of days, and you show me that with the passages that you've been sending me by email. So you're good. You're good. I think like you just have a couple of passages left or whatever, right?
Yeah, I was gonna ask you, what do you think the game plan should be? I mean, like right now, obviously my confidence is pretty went from low to high, but now it's like pretty high.
Yeah.
Should I do them? Should I just
So
leave it
how
be?
much do you have?
I have five passes total, so I think I have two here and three.
Yeah.
No, I have six passes. Sorry.
Got it. Yeah, so yeah, finish them by tomorrow and then don't touch cars at all until your test.
Finish them tomorrow and don't do cars Thursday. Then. Uh-huh.
Yep.
Um, yeah, I should call my testing center. Maybe they'll let me share my screen with you. So you could like watch me. It's kind of like I swear it's like Hawthorne effect, right? It's
Yeah, yeah,
like when
yeah. Yeah.
I mean I just yeah, now I have to replicate it without you watching me, without like knowing that you're watching anything I'm doing, you know? Like
Yeah,
it's
yeah.
just yeah,
No,
I obviously have to be on my best behavior, you know, as you're watching too.
yeah, yeah. So like perhaps my presence made you not look back at the passage so quickly and
Exactly.
that kind of thing, but I think that you will be fine because of the stuff that you've been doing, without like, on your own that you've been sending me the results of, where you got mostly all of the questions right. So, so yeah, you're just gonna finish up the car stuff and then you're done. You're done. Yeah, you've
So
reached,
there was
yeah, you reached the level that uh what that that
I
that you need to be. Yeah.
I yeah, I mean I hope I mean at this point this was like literally the shot this was like the biggest shot in the dark. Just like
Hmm.
the final just like push and it you know,
Yep.
with cars especially like
Yep. Yep. Yep.
yeah. Well okay, there was that one passage, it was about tragedies. I don't know like what do you think? Should we go over it? It was the one I got 7 out of 8 on.
Yeah, I mean, you only got, I know you want like, yeah, we can absolutely go over it. Um, but you got like, yeah, like one question wrong, right?
Okay. No, because there was that I wanted to go over, but there was also one other physics topic.
Hmm.
Um,
Yep.
so okay. Let's do the physics one first. And if anything, maybe we'll just end it there. But
Uh-huh.
so okay, I want to make sure I definitely like have this down. So let me find it first. But wait, okay. Okay, this is it. We did this before, but I just like really want to make sure that I have a solidified understanding of like the Lorentz force. Like both of the equations, QVB sine theta and like ILB sine theta, or it's a QVB cosine, it's QVB cosine theta, I think. I just want to make sure that I have a conceptual understanding. That's why I want to run it by you. As also the right hand rules, like both of them with the current as well as the um magnetic force and all that.
Okay. Now, what's the significance of cosine versus sine?
Okay, so um second. Headphone is a tangle. Okay, so sine is when something is parallel, I think. Wait, so I need to think. Um, so now, okay, we're using modern day vernacular. And so now, okay, so sine we use in torque, cosine we use in work. Now, torque, can't believe I'm forgetting this, but Usually torque, like sine is when something is perpendicular. I forgot. I forgot.
So, all right, which is which?
Sine is the black one, cosine is the blue.
Good. Now, like, oops. Okay. So, like, 0 degrees, 180, 360, right?
Yep.
What's this one?
Not 90.
90, right?
Yep.
So, as you go from 0 degrees to 90 degrees, what happens to sine?
It increases.
Yep. And at its maximum point, it's going to be 1.
Yeah.
And so if you're going from 0 degrees to 90 degrees with a sine term, you're going from 0 to 1. So sine is maximized at 90 degrees. And then you can see cosine is starting at, like, when it's the angle is 0, it's starting at a height of 1.
Hmm.
And when it gets to 90 degrees, the cosine term is at 0, like the height of 0.
Okay.
Yeah. So that means that if something is perpendicular, your sine term is going to be 1, and if something is uh parallel, which means a 0 degree angle, cosine of 0 degrees is 1. So that can help you remember. So work is going to be when the force and the distance that you're moving something are parallel, and that's why it'll be like FD cos. And torque is going to have a sine term, which would mean that you want it to be at 90 degrees in order for a sine term to be 1.
Hmm.
Yeah. So now, yeah, you said QVB sine theta.
Yep. And then there's ILB, I guess cosine theta. I don't even remember.
So now this has a sine term in it, which means it's favored at a 90-degree angle. And that 90-degree angle is what's between, like, let's say this is our moving charge with V here. Like, it must be perpendicular to the magnetic field. So let's say the magnetic field is this way, or more often it'll be like kind of like either coming out of the page or into the page. But yes, they will be like, yeah. So if you are dealing with something that's perpendicular, you would want there to be a sine term. If you are dealing with something that's parallel, you want to be dealing with a cosine term.
Hmm.
Yeah.
Okay.
So for this question, what do we do?
I mean, I remember it's none, but well, okay, enters with a speed of 500 kilometers per second, and it asks for the magnitude. What quantity, if anything, whose magnitude must be known, like to calculate the speed. So here they give us the speed, but magnitude it also includes direction, I think, or
Oh,
like it's no velocity includes direction.
mhm.
So well, in QBB sine theta, like Q is
The charge.
wait, but they already give us the speed, so like The speed is ready, like we have the speed. If they ask for velocity, right, then we would need some stuff because the velocity would change when it comes to a magnetic field because velocity includes direction. But because they're asking for speed,
Hmm.
there's nothing that needs
I see.
that. No, there's nothing we need.
No, no, you're right. You're right. Okay, yeah, yeah. Because yeah, this charged particle is going to be moving in a circle, right?
Mhm.
Like with a charged particle that's moving within a uniform magnetic field is going to be doing, it's going to go into a circular motion. But I think what you're saying is the trick of this. It's that yes, if something is moving in a circle, its velocity is changing because the direction is changing, but the speed, which is not it's a scalar, so it doesn't have a direction. Um, the speed is not going to be changing because only the direction is changing. So yeah, the speed is the same, and by extension, right, we could say that um that this charged particle that enters into the uniform magnetic field at this speed uh is going to be conserving is going to have the same kinetic energy as well.
Same kinetic energy, but kinetic energy includes velocity, not speed.
Yeah. Uh you're squaring the velocity term, so
Oh yeah.
the the sign is going to kind of like,
Mm-hmm.
get rid of that a bit. Or
Okay, but how about ILB, that equation?
um current, length, magnetic field strength. Um have you seen, like, I wonder if I like, have you seen that on like
A lot, like really not much. I mean, it's just a formula I know and I associate with this QVB sine theta.
Mhm.
Uh, I guess what might be a little more relevant though is the right hand rule, which I think is pretty relevant because I mean there's two right hand rules, but like knowing those as well, how to apply them,
Yeah,
especially the current one because that one I'm a little less familiar with.
got it. So let's say that we have,
Oh wait, and sorry, one more question. The
yep.
Lorentz force, is that just referring to QVB sine theta?
No, it's the sum of the electrostatic force and the magnetic force.
So the magnetic force is that QVB?
Yep.
And what is the electrostatic force? That oh well, wait, no,
You
that's it's Q1 Q2 K over R squared.
yeah, yeah. And if it's an it's if it's so like that's for like the point if you have like 2 point charges.
Hmm.
Um but if you're within a uniform electric field, it'll just be Q and then capital E being the electric field strength. It's kind of like, so like this is that, and then this is
Hmm.
this. And so if we have like 2 point masses, like we would use this formula on the right. But if we're on like Earth, um, these values turn into little g. And so that's why this turns into mg, where
Hmm.
g is not just the acceleration due to gravity, but it's the gravitational field strength.
Hmm.
So now this is going to be, so now like this will be little g, which is the gravitational field strength of the uniform gravitational field on Earth's surface. This is the uniform electric field uh for something. And
Okay.
mhm.
Uniform like electrostatic force is QE.
Yeah.
Okay.
Yeah, that would be the force of a charge. That would be the electrostatic force that a charge experiences in a uniform electric field.
And so the Lorentz force combines QE plus QVB sine theta.
Yeah.
And when the what's that thing when it's like perpendicular does no work? Or like when
Hmm.
you know
Yeah.
what I'm referring to? What is that again?
Um, I mean, like if something's perpendicular, and if work is FD cos theta, then cos of 90 will be zero, so it's gonna be zero, like zero work if it's perpendicular. That is that what you're talking about? Or
Um, like the fact that the work done on a moving particle is zero because something's perpendicular, like the Lorentz force.
yep. Oh, so okay. The Lorentz force includes the electrostatic force and the magnetic force. So if the angle between like whatever the magnetic field and the movement of that charged particle is 90 degrees, you're going to have that magnetic force. Um but it won't be doing any work, but your electrostatic force does not require you to have a 90-degree angle. So you will still, if you're doing, you would still be doing, work, except the work will be due to the um, electrostatic force.
Remember this question? Yeah, I remember the discrepancy. It was that UWorld regards the Lorentz force as not including electrostatic force. But this is what I was referring to. It's just UWorld has a like uh, they define it as just QVB sine theta, although I guess it should also include electrostatic force. But that was the question I was talking about, how like work done will not change.
No, so this is because this question is saying that there's only a magnetic field.
Oh, okay. Okay. Got it.
So like that mass spec what is it? Yeah, Jack Weston um passage here.
These are both from UWorld.
Uh-huh.
Okay.
So yeah, in the link that I just sent here, you're gonna have
Hmm.
the actual Lorentz force. Um yeah, let me know when you have it. Yep,
This?
yep. So Lorentz force, we can see, is a net force on a charged particle moving through an electric field where capital E is the electric field strength, and magnetic field where capital B is the strength of the magnetic field perpendicular to the velocity of the charge and the magnitude of the charge. So you see how it's both? It's a sum of the two.
Yep.
And then we have figure one, this thing called a velocity selector. And now this has an electric field going up from the bottom plate to the top plate, right?
Hmm.
And by convention, electric field lines go from what to what?
Positive to negative.
Good. So this uh, positively charged particle should experience an electrostatic force in which direction?
Uh, well, it's positive. It's gonna want to go down. Wait. It's gonna go up.
Yep, because this stuff would be positive,
Positive.
be negative. So that
Let's
and
do the whole passage.
what's up?
Let's do this whole passage. This is like perfect. This is what I wanted.
Okay.
Yeah.
So now okay, so now in figure one here, we also have this magnetic field B that's coming out of the page. So Um, so now let's talk about the right hand rule. So there's two of them, I guess. There's the right hand rule that um okay, so first of all, since QVB sine data or whatever, like you're having uh it in three dimensions, that's why we have to use the right hand rule like in the first place. But yeah, essentially your thumb is gonna be point like you're gonna basically, start off with your hand kind of like this, so that this is perpendicular to this, and then they're also both going to be perpendicular to like
Yeah,
imagine
yeah,
out of my palm. So yeah, if
yeah.
you have your thumb is going to be in the direction of that moving charge, um, moving like positive charge, by the way. Uh, your the rest of your fingers are going to be pointing in the direction of the magnetic field, and then your palm is going to be pointing in the direction of the uh,
Force?
magnetic force. Yeah.
Perfect. That's how I remember it. Okay.
Yeah. So what would it be for this in figure one? The magnetic force.
To the right?
So show me what you're doing. Uh,
Like,
so the thing is moving the thumb you want to be.
oh, wait, 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 wait. Oh my God. I was thinking about it moving up, like to the negative charge, to the negative thing.
Uh-huh.
So wait, velocity is okay. So hold on. It would be down.
Good.
So wait, I accidentally messed up. So I was thinking that the particle would be moving up because it's going towards the negative.
Yeah, that is indeed the electrostatic force
Mm-hmm.
that is pulling it towards the negative plate on the top.
Mm-hmm.
Um, but there's also that magnetic force, which is pulling it to the bottom, right?
Mm-hmm. And so when we see the V, I mean, we should assume it's the magnetic force because I mean QVB is in the that's right.
All right.
Like
Yeah.
in this type of problem, like we should just assume that it's the V is part of the QVB equation, like when it's written.
Uh, sure, sure. A moving charge is required for a magnetic force. If it wasn't moving, you wouldn't have the magnetic force. So if a charged particle is moving with a certain velocity, and if there is a magnetic field present, because the QVB needs the B part too, then yeah, there's going to be a magnetic force. Yep.
Okay.
Good. Um, Okay. And so yeah, so this is something so this is a good so this is like a perfect example of the Lorentz force because it's including both uh electrostatic force and magnetic force because there's both an electric field and a magnetic field.
Hmm.
And that's what enables this particle to move in a straight line to the right. This entire thing is called a velocity selector, and before it would be something like this. Oops. This is an electric field only. So now I wrote this positively charged thing, like without the V
Hmm.
and also without the magnetic field. But if you had a magnetic field, well, regardless. So what happens in this thing that I drew?
Okay, hold on. Before we get into that one thing, so
Yep.
what I'm a little confused about is how is the particle able to travel, like if it's going if the force of like so the Lorentz force it's going to the right or no, it's going down.
Uh,
Like I'm just confused if the electrostatic force is pushing it up to that negative top, but
yep.
then F of B is going down.
Yeah,
Like I don't understand what's going to be with the particle. Like it's kind of like tug of war.
yeah, yeah. So the this thing is called the velocity selector because if there was, for instance, a larger electrostatic force, this will go that way and like hit the plate. If there was a stronger magnetic force, it'll go that way and hit that plate. So what they have here is like they block this part out so that only particles with a specific velocity can go through this like kind of like slit here.
Okay.
And yeah, so that's the idea there. And before that though, we have this like a regular electric field only and a particle that's not moving. This should experience an electric force, right?
So you've drawn like this is just an additional particle,
Uh
or like well, I don't understand.
yeah, we could think of it as an addition like an additional particle, but also it's what's it's going to be, it could also be considered the same particle just before it gets to the velocity selector here.
Okay.
So this one here is what's going to happen to it?
Well, like I don't. I mean, it's like what is there some sort of charge on the top or bottom bar?
Oh, so here there's the left like plate and the right plate rather than above and below.
So ether lines going from left to right,
Yep.
positive to negative. Okay, it's gonna have an electrostatic force to the right.
Yes. So, and now let's say a chamber before that has the actual molecule, but you shoot some photon at it, that's going to be whatever beyond the workforce, cause workforce beyond the work function,
Mhm.
causing an electron to leave. So the first step is ionizing it.
Mhm.
All right. Then the next step is putting it in just an electric field. If you put it in just an electric field, the charged particle that doesn't have to be moving, right, will experience that electrostatic force, causing it to move. So that's how you get the particle that you're putting in the mass spectrometer to like actually be able to go from rest to some velocity, such that when it enters the velocity selector, it already has that v, the velocity.
Mhm.
So that's just what happens prior. So now once it leaves the velocity selector, it's going to be in an environment that is strictly a magnetic field. And that would cause that centripetal motion, which would let it, like, if this was elongated, like, it would hit something here, and it can also hit something here. And that the radius, or how far it hits on that, is gonna be related to uh the centripetal force and the magnetic force and stuff. So I'm just gonna erase this so that you can kind of see that, like, so they're saying here figure one shows a velocity selector which operates on the basis of the Lorentz force. In it, a charged particle with a velocity v is sent between two oppositely charged parallel plates. Um, blah blah blah. Essentially, just saying that this is the velocity selector where there's already a moving charge in it, as well as both the electric field and magnetic field. But if we go down to figure two, you can see kind of like, okay, so like starting out over here, and we have some electric field here, and it's just an electric field, so it's kind of like what I was drew here, where the electric field is this way, and it causes this to start to move.
Mhm.
That's the electric field. And then here could be like the velocity selector, which would let the particle go through like this little slit. And once it leaves that, it enters a region of magnetic field without there being an electric field. And that's when it starts to like deflect. Um, and like, so if this detector wasn't here, it'll just keep moving in a circle.
Hmm.
But with a detector there, it'll hit the detector, and the higher mass it is, the longer this radius becomes. So, like, if it hit here, right, it'll be of a higher mass. And
Hmm.
so, what they do on the bottom of this passage is they equate that magnetic force to the centripetal. Yep. So, what they're doing is like, so QE plus QB BB, whatever, sine of theta, plus, or rather equals the centripetal force, something like that. Now, there's no electric field in this region where it's just a magnetic field. So it'll just be this is equal to that. And then you just rearrange. You can divide B on both sides. You can, I guess, do multiply R on both sides and then divide QB on both sides to get MV over QB. And now this shows the relationship between that radius and mass. So, like, yeah, so something that's a smaller mass would have a smaller radius and get deflected like more uh in a more extreme way, I guess, for it to hit like this detector. It's like when they were purifying like uranium 235 from 238. This is what they use. They put like, okay, this is for uranium 235. This one a little bit further out is for uranium 238. And the 235 with a smaller mass will have a smaller radius, hit and enter into this container. Uh, the heavier one would go into that container. So that's pretty much what this is. Yeah.
Okay. So now let's go through these questions real quick.
Yep.
Which of the following expressions, if true, would cause a charge traveling through the velocity sector to collide with the positive parallel plate? Positive parallel plate. Okay. Well, so this is what you were alluding to earlier, I think. But well, the positive parallel plate is the bottom one.
Mhm.
Um, so velocity E over B, but like what? Uh, okay, so the electrostatic force pushes us up. The the B pushes us to the right. Or
Pushes it to the right.
the QVB is to the right? Or is that the Lorentz force?
So this is already like this already has a velocity because of the thing before, which is just that electric field. So it's entering with a velocity, and the electrostatic force should make it, hit the deflect and hit the plate on the top, whereas the magnetic force would cause it to deflect and hit the plate on the bottom. So,
Okay,
yep.
the thing is, when we do the right hand rule, okay, the answer here has got to, why is it doing that? The answer here should be D.
So let's think about it first.
Okay, because okay, so I'm gonna say like when we do the right hand rule, what is that for? That is simply for QVB, right?
In the sense that QVB is the magnetic force. Yes, that's one of them. The other one is with the curl to just determine if something is, come like a magnetic field around a wire is like coming out of the page into the page, but yeah, the QVB is the magnetic force. Yeah.
So when this particle comes into this like velocity sector, it's moving to the right
Right.
originally.
Yes.
But as it enters the space, there's a force that's electrostatic that pushes it up, and there's also a magnetic force that pushes it down.
Yes.
And the Lorentz force is the combination of both,
Yep.
the up and the down in this case, right? Okay. Yeah, I just want to make sure that I understand. And so here, what I'm a little confused about is what they mean when they say E over B. I'm a little
Mhm.
I don't really understand that like notation.
Got it. So yeah, let's first think about it qualitatively or conceptually. So so if this hit the positive parallel plate, like what what can either cause that or be a result of that?
So if something hits the positive parallel plate, that means that the magnetic force was greater than the electrostatic force.
There you go.
So what I would think is that it's D.
Like let's write it out. So you're saying this is less than that, right?
Yeah.
Okay. Go from there.
E is less than VB.
Okay.
Okay. Uh, V is greater than V is greater than E over B.
Yep.
Okay.
Mm-hmm.
What would make D wrong though? Because we're not like including the velocity part.
Correct. Mm-hmm.
I just put that just so I can take a screenshot.
Mm-hmm.
Um, okay. Wow, you pulled this passage out just like from the your back pocket.
Yeah, this is a common one because it deals with like a common one that I bring up because it deals with Lorentz force and it's a good way to kind of like go over like the right hand rule and all that stuff. Mhm.
Yeah, because this is exactly what I like wanted. I want to go over that topic and yeah, that's good. Okay.
Yep.
Um, all right. Suppose that the distance is half between the parallel plates of the velocity selector. Okay. Half. What would be the effect of this charge on the path radius of positively charged particles that enter the magnetic field? Effect of this change on the path radius of positively charged particles that enter the magnetic field. Suppose this is so distance is halved, like I'm uh The path radius. Like, I mean, are they talking about this or this, you know? Um,
So, um, a radius would indicate that there's a centripetal type of movement,
mhm.
and that can only happen if, I mean, in this entire thing, if it's in just the magnetic field, whereas figure one is both the magnetic field and the electric field, which produces a straight line. So it's the magnetic field into the page region with the detector that causes that centripetal motion, which means that it can hit the detector in its centripetal motion. So they're asking if you cut the distance between like the parallel plates of the velocity selector, like here, like if you made them closer, how can that affect the radius of the thing, of the move of the uh um charged particle?
Mhm. So distances have, um, I'm like trying to think of an equation relationship, but it's like there's mv squared, v equals ed.
Mhm.
I, for- is that, oh, because I remember v over d is electric field.
Yep.
Yeah. But I usually think of that as for capacitors. Is that just for anything or?
Hmm.
So, okay, hold on. Q over dielectric constant or whatever that constant is called times A. Q over A times the whatever Greek symbol. That's also for electric field of a capacitor, right?
You're talking about like that thing?
Yeah, probably.
Um, permit permittivity of free space, I believe it is.
There we go.
Yeah, that's like for, I mean, yeah, it plays a role in capacitance as well as all these other things. And it's some constant. And even though we saw that one question that mentioned it, it wasn't like we were expected to know much about it. But yeah, it's something called the permittivity of free space. It's like
It's fine. It's,
yeah,
it's like I don't even want
yeah.
to get into that. Perpetuity free space. Okay, so V equals ED.
Hmm.
So V over D equals E. E is the electric field. Um, I what I don't understand though is you're bringing this up, but like they ask, they don't mention electric field at all in the um. So I guess you're basically, oh yeah, because it says parallel plates. So yeah, that would make sense, I guess. Um, but there's only a distance term. Okay, the distance is half, but QVB like okay, if distance is halved, the velocity is halved. Velocity, it's halved. Now that means that I guess the radius would be halved.
Did you say velocity, or did you mean like voltage?
I meant voltage.
Okay.
Shoot. Okay, wait. Then I yeah, I have no I don't even know.
Oh, we could rearrange it. So electric field is voltage over distance, and
Okay, this is halved.
electric field is inversely proportional to distance.
Yeah.
And then elect yeah. I think you can go from there.
Yeah, so electric field would be doubled.
Mhm.
So
And then we know that R is that.
okay. So electric field would be doubled and still I don't really know how to connect that to this.
So our electrostatic force we wrote was that. So if we increase, I guess we could also do um let's see. Electric field is oops, like that. Inversely proportional to charge. So if we have the distance between the parallel plates, we get twice as much of the electric field. If we have twice as much of the electric field, we have the charge. And if we have half the charge here, we have double that radius.
Okay, yeah, that's why I stopped doing Jack Weston. It's so hard.
Yeah.
Like,
This is just algebraic manipulation. But I'm
yeah, yeah,
gonna
yeah.
put a question in the chat and then we can have that be like whatever the last one. So here's the
Uh-huh.
problem in the I put it in the chat, yeah. Oh, let me erase my drawings.
You see it?
Yes.
Okay. What is the direction of the force on a negatively charged particle as it enters the magnetic field shown below? Like the force of the like magnetic field or the electrostatic field, electrostatic force or the magnetic force? Like what is it asking, you know?
Yeah, you can read it.
Okay. So I know what you're doing by the way. You're testing me on the fact that's negative. Um,
That's part of it.
yeah.
Uh,
Hold on.
but another part of it would answer your question about electric field or any of that stuff.
Mhm. Okay. See.
All right. Yeah. Plain.
So, this test right hand rule, basically magnetic force here. I realize it's actually there isn't really an electrostatic force.
Because there's no electric field, right?
There's no electric field. Yeah, and when I saw N and S, I'm like, wait, magnets, north and south.
Yep.
So when you have your hand, I mean, You do magnetic, you do the rule, whatever. Usually for positive, that's what the right hand rule's for, but because it was negative, I just inverted what I got.
Mm-hmm. Exactly. Perfect.
Yeah.
Good stuff. So yeah, I would say for homework, tell me if you have maybe you've seen this before, but
Okay.
two wires, currents going in opposite directions. Are these wires going to attract or repel? And then two wires going in the same direction, are these going to attract or repel?
Got it. Okay. The top one was an Altius question, I actually remember. But yeah, this is also good. This is good. Okay.
Yep.
Yeah, let's not forget to discuss that tomorrow. So,
Oh yeah, yeah. So awesome. So yeah, you're crushing it. Your cars is what you're doing. You reach that balance. You're good. So uh yeah, so tomorrow we don't even have to do much car stuff, but I will see you. Yeah, so I will see you tomorrow, okay?
wait, tell me how much the total was.
Oh yeah. Um you could just do like 150.
Okay.
Yeah.
Thank you so much for
Yeah,
everything.
of course.
Thank you.
Yeah, of
I'll
course.
see you.
All right, take care.